Okay, so welcome everybody. We're happy and proud to have here with us today Yakov Babichenko. He did his PhD in the Hebrew University and then a postdoc in Caltech, and now he's an associate professor at the Technion, Israeli Institute of Technology. He got the Krill Award for Research of Excellence in 2018, and he studies mainly adaptive learning and complexity of equilibrium. And he will talk to us today about optimal persuasion via B-pooling. And Yakov, the stage is yours.
Thank you, Galit. Thank you for the introduction and for inviting me to give this talk. So the talk is about optimal persuasion via B-pooling. This is a joint work with Itai Arieli and Ran Smorodinsky, my colleagues at the Technion, and with Takuro Yamashita from Toulouse. Okay, so let me jump directly to the model that we will study today. The model is essentially a Bayesian persuasion model with continuum of states where receiver cares only of posterior means. Okay, this is the model that this talk will be about. I will explain each of these terms. Bayesian persuasion is essentially a communication where the sender is a communication problem, strategic communication problem, where the sender is allowed to commit to his signaling policy before he knows the state, before the state is realized. Continuum of states, this is, I think it's clear. And what does it exactly mean that receiver cares only of posterior means? I will explain it in a few moments. Let me just maybe say that this is not the first paper that studies this model. In fact, recently there are quite a few papers that focus on this particular model. Maybe Dvorak and Martini is a paper entirely about this paper, but it is also indirectly or directly mentioned in quite a few other papers, as you can see. So, okay, so let me start with the model. Okay, so we have a single sender, single receiver, a continuum of state, one-dimensional continuum of state 0, 1, and a common prior, which is a distribution over the states. In this case, it's a distribution over the segment 0, 1. And now we have an abstract set of signals, which we will identify also with the segment 0, 0, 1 by the direct correlation principle, essentially. But we have, in principle, we can have an abstract set of signals. And a signaling policy of the sender is essentially a distribution, a mapping from the states, which in this case is the segment 0, 1, to distribution over states. Once a receiver observes a signal, he forms a posterior about the state. So he starts with the prior F, and after observing state S, his posterior, let's say, let's call it, will be Q of S, which is, again, it's a distribution over the state. The posterior mean assumption that I just told you before is the following. Assume, let's consider two different distributions over the states, or two different posteriors. One is Q and the second is Q prime. And if it is the case that the expectation of Q equals to the expectation of Q prime, then the assumption tells us that receiver will take the same action. His best reply action will be the same, and since therefore his effect essentially on sender's utility will be the same. Okay, so this is the posterior mean assumption. In a moment, I also will give some interpretation for this posterior mean assumption and see where it naturally arises. But before that, let me just remind you or tell you what is the timing of interaction in the Bayesian persuasion model. So as I said before, in a Bayesian persuasion setting, sender has the commitment power and he can commit to a signaling policy before state is realized. So he commits to a signaling policy. Then state is realized according to the common prior. Signal is realized according to the committed policy. Receiver observes the signal, forms a posterior, and takes an action which determines sender's utility. Okay, so this is the kind of standard Bayesian persuasion model. Okay, so now let me say a few words about the posterior mean assumption that I just said. So which motivation can we give to this assumption? So Dvorak and Martini gave several motivations that follow essentially from the risk aversion of the receiver in their case, which is a principal agent in a principal agent models. It might they have several examples where this assumption is natural. In investment recommendation, it also can be natural. But let me give you yet another motivation for the problem, for this risk, for this posterior mean assumption, which has not been mentioned in Dvorak and Martini, and also not in the other papers, and I think it's quite cute interpretation. Let's consider a standard Bayesian persuasion setting, but not with a continuum of states, but rather with just binary state. The original state was called omega, and here I call it theta. Okay, theta is a binary state. But now, instead of assuming that the sender is fully informed about the state as it is assumed in the standard model, in the standard Bayesian persuasion model, it is assumed that the sender, his policy is a mapping from the states to signals, which means that sender essentially knows the state. Instead, let us assume that sender only receives some information about the state. Namely, he's also partially informed. He doesn't fully know the state. So theta is just a binary state, either 0 or 1. Omega in this case, which is sender's belief about theta, which is commonly known to be distributed according to F. Okay, so how this can arise essentially from some information, commonly known way that commonly known distribution of posteriors, namely sender is partially informed about the state, and the way the sender is partially informed is commonly known by the sender and by the receiver. Okay, now receiver's utility is essentially what I want to emphasize. Let's focus on a model where receiver utility is obviously a function of his own action, but and also of the binary state. Okay, so his utility is only a function of the binary state. He doesn't care what is the posterior of the sender, and now receiver's belief about theta is precisely the expectation of Q of S. Okay, so this is another nice, cute interpretation of the posterior mean assumption. Namely, if you take a standard binary signal Bayesian persuasion problem, but add to it a modification that sender is not fully informed about the state, but rather receives some partial information about it, you get exactly the model that we are going to study today. Okay? So posterior mean assumption is satisfied in this model. So from here I'm going back to the standard, to the model where with continuum of states, which is essentially equivalent to the partially informed, but this was just one interpretation. What is our objective in this talk? Essentially, right, so maybe the most natural question that we can ask is to gain understanding on how to solve persuasion problems with continuum state space. Okay, this is maybe the most natural thing that we would like to do. But let me mention another one. Our second objective, which in fact will be the first in order of the presentation, is to characterize the structure of optimal policies in such problems. Okay, and the one, I think, independently, it's a natural question to ask, but moreover, we will see that such a characterization will also assist us in gain understanding on question number one, namely how to really solve persuasion problems in continuum state space. Okay, and maybe let me say a few words. What exactly do I mean by saying that what a characterization of optimal policies structure? So essentially, what we are looking for is to find as small as possible subset of policies. Pi is the set of all policies. From there, we want to look on only some restricted subset, such that every persuasion problem will admit an optimal solution in this set. This will tell us that essentially, okay, we found you always can pick calligraphic P to be exactly pi. Yeah, but essentially we want more than that. Yeah, we wanted this set to be as small as possible. And later I also will convince you that the answer that I give you is in fact the smallest possible. Okay, we will have a characterization, and that essentially will pick the smallest possible subclass of policies. Okay, so just to make you some reminder and also to introduce this, maybe not the most standard question of characterization of optimal policies, let me go quickly over the simple case of binary state persuasion problems. In this case, the set of policies that characterizes optimal policy is the set of all binary signal policies. Okay, we have many policies in this case, but binary policies are sufficient, and moreover, they are the smallest possible set. And let me try to convince you in that. Okay, so how we solve Bayesian persuasion problems in binary state space. Okay, so the notion of concavification, it essentially tells us everything that we need to know about the binary in order to solve a binary state persuasion problem. And let me demonstrate it by an example. Okay, so let's draw a curve that corresponds to the utility of the sender as a function of receiver's posterior. Okay, if receiver posterior is 0.6, for instance, this point, then he will take some action, and with this he will take his optimal action, and this action will yield a utility of this value for the sender. Okay, this is the function that we draw. And by the way, from the you can see from the picture that essentially in this specific problem we have a continuum of actions for the receiver, right? We can see it because sender gets infinitely a continuum of different utilities. So along all this talk, we will not restrict ourselves to finite number of actions for the receiver. Okay, it can be an arbitrary set of actions for the receiver. Okay, so essentially what Aumann and Maschler have suggested, and it was later used in the context of Bayesian persuasion by Kamenetsky and Yakov, is the notion, they suggested the notion of concavification, which is the minimal concave function that is pointwise above this utility function. You can see it here in red. And in order to understand what is sender's optimal utility in the persuasion problem, it's essentially the value of the concavification at the point of the prior. Okay. Moreover, we can also deduce from this picture what is the optimal policy for the sender. His optimal policy will be to use two signals that will be essentially, the prior here will be split into two atoms, one on this red point and the other on this red point, and essentially his optimal policy will induce two different posteriors for the receiver, only this one and this one. Okay. So this is essentially summarizes essentially the solution for the binary state policy. So structure of optimal policy in basic persuasion, in binary state persuasion, is essentially that binary signals are sufficient to persuade optimally, right? We can see here that for the concavification we need only at most two points. And any pair of binary posteriors can be the unique solution of a persuasion problem, whereby any, I mean that one posterior obviously has to be above the prior and the other has to be below the prior, right? Because these 2 points has to satisfy essentially the expectation of the posteriors must be equal to the prior. So, so obviously one should be above and the second should be below. Why do I mention bullet number 2? This is exactly to show you that we found the smallest possible set. Okay, our objective is not just to come up with some set of policies, because maybe among the binary signaling policies there are many, we can significantly reduce it, and in fact maybe many of the policies there are not needed. So the second bullet shows us that this is not the case, that indeed every binary posteriors can be the unique solution of persuasion problems, and therefore we essentially need all of them. Okay, so this is what I mean by characterization, and our goal is going back to the sorry, what? And sorry. So there were 2 slides that I forgot to erase. So yeah, so my mistake that there was. Okay, so let's proceed from here. So so going back to our question, what is the structure of optimal policy in the continuum state space problem, or also in the partially informed sender problem? So maybe the first approach to tackle the problem is this is just a standard Bayesian persuasion model with the state space 0, 1. So use the concavification result in this space. Unfortunately, in high dimensional spaces, the concavification result is not very informative. Namely, it still remains to be true that the optimal utility that the receiver can get is a concavification of the function, but it's a concavification in an infinite dimensional state space. And this notion is not very convenient to work with, and in fact, it doesn't tell us, it's hard to deduce from it some meaningful insights about the problem. So we need a different approach, and the different approach, which has been suggested in previous literature in this context, essentially kind of focus, it's a mean preserving contractions approach. What is essentially due to the posterior mean assumption, that means that, I remind you, it tells you that the receiver will take exactly the same action if for 2 different posteriors with the same posterior mean. Therefore, sender cares only about the distribution over posterior means. Okay, he doesn't care exactly what will be the posterior of the sender in each of the cases. He only cares about what is the distribution over posterior means that his policy induces. Okay, so which distribution over posterior means are implementable, namely can be implemented by some signaling policy. So this question has a very clean characterization. A distribution over posterior means is implementable by some signaling policy if and only if G is a mean preserving contraction of the prior. Okay, so this observation essentially helps us in understanding better the persuasion problem, because we do not have to look on distribution over posteriors, which is a distribution over distributions of 0, 1, but instead we can look on mean preserving contractions, which are only distributions over 0, 1, a simpler object. Okay. Our goal is to find a simple class of mean preserving contractions that is sufficient to solve optimally every persuasion problem. Okay, this is exactly what I said, a characterization essentially, to find as small as possible and also as simple as possible the class of mean preserving contractions. The first, maybe the first in simplicity, let me suggest you one class of simple mean preserving contractions that is sufficient to persuade optimally. Sorry, that maybe, but at least it's quite simple class, is that of pooling contractions. Okay, so to understand what pooling contractions are, let me draw you a picture, demonstrate it to you by a picture. Okay, we have here the prior, which is a distribution over 0, 1, and a pooling policy. Essentially, what it does, it looks on. It defines some subset or some that's countably many or finitely many intervals, and inside this interval it only reveals that the state is inside this interval, which will pull all this entire segment to an atom on this point. Okay. And the same, so in each interval, it will reveal only that it appears in this interval. Outside of this interval, I will the policy reveals exactly the state. Okay, therefore, the mapping is essentially identity, and here it maps all the entire interval into an atom. Okay, and maybe the first question is, are pooling contractions sufficiently rich to optimize every persuasion problem? By the way, the class of pooling policies is indeed quite a simple class. And for instance, in the classical paper of Kleifer and Sobel on chip talk, essentially the type of policies that are optimal in their setting are essentially pooling policies, where indeed you reveal only in which interval, to which interval it belongs. The answer to this question is unfortunately no. This class of policies is not sufficiently rich to optimize every persuasion problem, and let me show you a counterexample. Let's think of the prior to be uniform on 0, 1, okay? And sender's utility is this curve. All that is important about this curve, that it has two global maxima, one at the point 1/3 and one at the point 2/3. Okay, so essentially an optimal policy in this setting will be to contract somehow the segment 0, 1 to 1/3 and to 2/3. Is it possible to do? Is it possible to contract 0, 1 to 1/3 and 2/3? Yes, it is possible. Let me show you one way to do it. If you pool the segment 1 over 12, 7 over 12, which exactly has a mass of half, into 1/3, right? If you reveal to the sender whether the state is in the segment 1 over 12, 7 over 12, or not, then his posterior here with probability half, his posterior will be his posterior mean will be 1/3, and with probability half, his posterior mean will be 2/3. Okay. So it can be done, but it is impossible to do it via pooling policies. Roughly speaking, the intuition you write is that low segments, you have to pool them somehow. You are allowed only to use disjoint signals and intervals and pool them. So the only candidate to pool to the low posterior is the segment 0 to 1/2, but but 0 to 1/2 is contracted unfortunately to 1/4 and not to 1/3. Okay, so it is impossible to do it with pooling policies. So the next kind of the second in simplicity class of mean preserving contractions is that of B-pooling contractions. This is also the title of this the talk. So it will play a significant role in this talk. What are the B-pooling contractions? Essentially, we do everything quite similarly to how we do in pooling, and only allowing for one additional flexibility. As previously, I partition the interval 0, 1 into countably many intervals, and I have the complement of it, which is the other point. But inside each interval, I'm allowing either to send a signal, a single signal, which will pull all the posterior into its expectation, or I'm allowing also to send two signals inside inside an interval, and then it may create two atoms on this inside this interval. Okay, so this is the picture of a B-pooling contraction. It has pooling intervals and it has B-pooling intervals. Okay, let me tell you the concrete definition of B-pooling, not with a picture. So essentially, we are talking about mean preserving contractions of the prior. So a mean preserving contraction of the prior G is a B-pooling contraction if there exists as a countable sequence of intervals, countable of disjoint intervals. Yeah, I forgot to say that those should be disjoint intervals. I didn't write it. Such that on each of these intervals, the distribution G is a mean preserving contraction of the distribution F. Okay, this entire segment is mapped into some binary support distribution, right? And G is a distribution with support of at most 2. And the second property is that outside of all these intervals, G coincides with F. Okay, the distribution is exactly the same. The identity mapping means that essentially the distribution doesn't change. Okay. So our main result is that this class of policies is sufficient to optimize every persuasion problem. Every persuasion problem admits a B-pooling contraction optimal solution. And our second main theorem, just to convince you that that essentially we picked the smallest possible subset, is also shows that for if you give me a B-pooling contraction, there exists some persuasion problem, namely a utility with in fact, for every prior there exists a utility, for which this contraction is the unique optimal solution. Namely, we cannot, it's not that we found some subset of policies that is sufficiently rich to solve optimally every problem. It's exactly the smallest possible subset of policies that has this property. Okay. I will not tell you details about the proof of theorem 2, but let me tell you about theorem 1, about the kind of the idea. In fact, it's almost a proof. The idea of the proof of theorem 1. So let's think again about what essentially is Sanders' problem. Sanders' problem is to maximize, right? What if he by colotilling and colotilling and also by Genskov and Kamenitsa, and essentially he is able by pooling policies to produce any mean preserving contraction. Okay, any mean preserving contraction of the prior is something that he is able to do. So among all these mean preserving contractions, he wants to find the one that maximizes his utility. Okay, so this is essentially Sanders' optimization problem: maximize over all the mean preserving contractions the expected utility. Okay, so this is what he's.
Yakov.
Yes.
Sorry, just a clarifying question. When you the Sanders policy is a deterministic function, must be a deterministic function of the state?
Good. So the answer is no. It does. So the question, maybe let's go back to this picture. The question was whether we restrict our attention to deterministic policies, namely without tossing coins in each of these continuum of states, or we allow also. So at this point, I do not want to impose such a restriction of deterministic policies. In fact, deterministic policies are quite rich in this setting, and you can, for instance, implement every B-pooling contraction also by deterministic policies. You do not need the randomization for that. But yeah, so this is the question. But the issue of pure versus mixed signaling policies will come later in the talk. But
what I don't understand is, suppose the prior, the Sanders prior has only finitely many points in its support. How can you make such a? How do you implement a pooling policy?
Right. So yeah. So for the purposes of this talk, let's think of F as non-atomic distribution. Okay. But if you want a generalization of the notion of B-pooling in the context of in cases where you do allow atoms, then you obviously need to allow the sender also to split mass and indeed to use mixed strategies. Namely, an interval can be located exactly in some interval, and part of the mass of this atom can belong to one subset, and the other part can belong to the second. Okay.
Okay.
You do need indeed for cases for the case where F is atomic, you need mixed signaling policies to implement any B-pooling contraction.
Okay, thanks.
So the class of mean-preserving contractions is essentially a convex and compact set in the weak topology in the space of distributions over 0, 1. And the objective is a linear objective, right? Expectation is a linear objective in this context. So by Bauer's maximum principles, it achieves a maximum in an extreme point. Okay, we have an infinite dimensional space, and we have a linear objective over this infinite dimensional space. So the maximum is obtained in an extreme point. So essentially, our theorem 1 is based on the characterization of mean-preserving contractions. And to the best of my knowledge, we didn't find this characterization in previous literature. By the way, there is so let me just tell you, the extreme points of the mean-preserving contractions are precisely the B-pooling contractions. Okay, this is the characterization of what are the extreme points of mean-preserving contractions. And this proposition might be of independent interest, and in fact, it has many other uses. For this exact characterization also has been independently proved by another paper from just independently in parallel to ours by Kleiner, Moldovano, and Stark, and they show quite a few other very interesting uses of this characterization in the context of optimal delegation and in the context of mechanism design, and in particular in ranked item auctions. Okay, so this is as you can imagine, right? So since mean-preserving spreads and mean-preserving contractions play quite central role in different economic models, it's indeed has quite a few uses if once we understand the extreme points of it, and Kleiner, Moldovano, and Stark showed quite a few of them in their recent paper. Yeah, and independently of us, they also came up with this characterization of the B-pooling contractions. Okay, so this is now I talked about characterization, but essentially the goal of one of the goals now what I want to try to show you is that essentially using this characterization, we maybe are able also to solve or to gain some understanding about how to solve the persuasion problems. So one approach, which is not new, is a convex programming approach, and I will go very briefly about this result, but then I want to talk about another technique, or you can say algorithm for solving persuasion problems that is based on guessing Dvorak-Martini price function. Okay, so what is Dvorak-Martini price function and what does it mean guessing it? I will explain you in a moment. Let me go very, very briefly on the convex programming approach. So a special case that we can consider, which corresponds to the case where a receiver has finitely many actions, is the case where sender's utility is piecewise constant and it has n pieces. Okay, so this corresponds to the case where receiver has n actions. So in this case, we know there exists a polynomial in n algorithm for finding the optimal policy, and this algorithm is based on the convex programming approach, it is similar to, it improves upon a result of Candogan, who also used convex programming, who proved that same result for the case of monotonic piecewise constant utilities. In fact, we show that monotonicity is not needed there, and it can be solved without, that monotonicity is not an issue that is needed there. And obviously, once we have an exact algorithm for piecewise constant functions, we can always apply to solve any, let's say, Lifshitz function just by approximating the function by piecewise constant functions and applying this algorithm. Yeah, so this is in terms of kind of computational algorithmic approach. But let me tell you about the second approach, which is by solving persuasion problems by guessing Dvorak-Martini price function. One of the reasons why I think it's needed is essentially that the convex programming algorithm, okay, it's an algorithm, but essentially we do not, maybe the computer can solve it, but it doesn't visualize what is the solution, etc. And I think one of the nice things about the Dvorak-Martini price function, except for the fact that it might solve explicitly functions, let's say smooth, for the case where you use a smooth function, which is not included in these two results, not approximately, but explicitly solving functions. It also visualizes and essentially shows us what and how an optimal policy should look like. Visualization is similar to how, in the spirit of how, let's say, concavification, one of the nicest things about it, that essentially we can draw a picture that essentially tells us everything about the problem, unlike, let's say, the convex programming approach, that where we cannot draw anything, which you can just write a computer program. Okay, so let me tell you what Dvorak-Martini price function is. So a function P from 0, 1 to the reals is called the price function of G in the problem F, U. F, I call it is a prior. U is the G is the mean preserving contraction of F. And now we have another element P, which is a price function. And it is a price function if it satisfies all the above conditions. First of all, it has to be pointwise above the utility. Second, it should be convex, okay? Unlike concavification, convex, not concave, convex. A third property, that the support in places where G has positive support, we must have identity between the price function and the utility. Okay, and finally, the last property is the expectation of the price function over G and over F should be equal. Okay, I think the best way to understand this property is by drawing you a price function. Okay. So think of G to be some mean preserving contraction of, here we mean preserve 0 to Y is contracted to these 2 points. Y prime is contracted to Z3. And essentially Y prime to 1 goes essentially by identity. Okay, it's not contracted at all. So so as we can see, this black function is pointwise above the function, the utility function. The black function is pointwise above the blue function. Second, you can see that P is convex, right? You can see that it's convex. Third, in all points where in the support of G, which consists of these three atoms, Z1, Z2, Z3, and the segment, the tiny segment Y prime 1, which is this segment, over this entire segment, we have that the functions coincide. Finally, to see the last property, we can just look at in each segment separately. So in the segment 0 to Y, since the expectation of since the function P is linear, so and the mean preserving contraction obviously preserves expectation. So essentially, the expectation of let's say the distribution according to f of this linear function and according to g is some point here in the middle. The same for here, according to f and according to g, it will be precisely this point. And here we obviously will have this property. So this is an example of a price function. Okay, so the black function is a price function of the function of the blue function. And what is the main result of Dvorak and Martini? If some mean preserving contraction admits a price function, then necessarily G is optimal. Okay, and the second main result is that every optimal G admits a price function. Going back to this example, it means that essentially the policy that B pulls the segment 0 to Y to Z1 and Z2, and it pulls the segment Y to Y prime into Z3, and it fully reveals the state in the segment Y prime to 1, is an optimal policy for this problem. Okay. So the main theorem of Dvorak and Martini is essentially that every optimal solution admits a price function, which is the second point, and also that if G admits a price function, then it is also optimal.
May I ask a question now, or shall I wait till the end?
Sure. It's a great time for a question. Yeah.
Go please back one slide.
Yeah.
Yes, here, if you, between 0 and Z1, if you made the function P to go, what I basically mean is that you can still be convex if you go like down and then up linearly. But actually, no, here it looks, but what you can, let's say from a little bit left to Z1.
A little bit left to Z1.
Yes.
Yeah.
You can just go linearly to somewhere in the middle between 0 and Z1 to the lowermost point, and then you can go up to 0, right? Linearly.
Approximately as I draw it here?
Yes, something like that.
And then you will go here, and from here you will not have a way to continue it.
Yeah, you're right. And so it will eventually be not convex. You're right. Yeah. Thank you.
Yeah. Okay. Yeah. It's indeed. Yeah. This is exactly my next slide. Will show how to play with this figure in order that it will be satisfied. So the interpretation of the price function that Dvorak and Martini gave is essentially some very nice story of Bayesian equilibrium in a persuasion economy. So this was kind of their interpretation of this result. Let me tell you maybe another kind of natural interpretation of this result is, let's say that someone you tell me that, you know what, the optimal thing to do here is to contract the segment 0y to Z1 and Z2 to contract to pull the segment y prime to Z3 and to fully reveal the state from y prime to 1. And I'm telling you, I don't believe you. Please convince me that this is the case. How can you convince me? Okay, so exhaustively searching over all the policies is something non-efficient, right? But what is, so this is in some sense a succinct evidence for optimality of G. if you provide me this function, now I know that there is nothing better than what you just said. Okay, so this is another interpretation of this result. Okay, so what I want to show you is essentially the plan is to show you how to find the price function, and obviously once we found the price function, we can easily deduce from it what is the optimal policy. Optimal can be deduced quite easily from the price function. The challenge is to find the price function. I showed you a picture with the function and with the utility and with the function, but typically we just get as an input the utility, and we have somehow to guess what the price function is. Okay, so our proposition, which is not very hard, essentially it yields, relies on Jensen inequality, tells us that the price function of Dvorak-Martini is linear over the pooling and the B-pooling intervals. Okay, this is so the main theorem says that essentially in every optimal policy we have these intervals, and essentially there are only either pooling intervals or B-pooling intervals. And in the context of Dvorak-Martini price functions, it tells us that the price function is linear over these intervals. Okay, so it was not a coincidence that here we draw a linear function and that here we draw the linear function. Okay, so now the question is how to solve a problem, right? So essentially what we get as an input is this type of a function. Okay, let's assume that the prior is uniform. Okay, so the first thing that I want to do, recall that the function has to be pointwise above the function. It is linear by the proposition, and so just by these two properties, if we have some B-pooling interval, an interval that essentially touches the function in two different points, then it must be what I'm calling double tangent. Double tangent is a point that touches the function that is pointwise above it and that touches it exactly in 2 points. Okay, so in this, the advantage essentially is that we do not have too much double tangents in any picture. This is quite so typically the number formally, if the number of convexity concavity regions is n, then you will have finitely many double tangents, maybe n square at most or something like this. Okay, so you do not have too many double tangents, and moreover, not all double tangents are legal, and let me tell you why. Okay, so the idea is that to guess where the B-pooling intervals are located by drawing the double tangents. Okay, so the green is indeed legal one. Why this L2 is illegal? Because these 2 points are located too extremely far from each other. Namely, there is no mean preserving contraction. Even if we take the entire this segment, there is no mean preserving contraction that essentially will have these 2 points as the support. And similarly also for L3, it's these 2 points are too far from each other. Here they are sufficiently close to each other. Okay, so once we have in mind once we guess what where is located the B-pooling interval, now all we have to do is essentially to try to complete the picture with drawing only pooling intervals and full revelation. So how a pooling interval will look like? A pooling interval must touch a point exactly at one point, and in the case of uniform prior, this point must be located exactly at the center of this interval. Z3 should be exactly the average of y and y prime. Okay.
Yakov, could you go back a slide and explain again what you mean by those being too far, by the peaks being too far?
Yes. Great. So if you let's take the example of the uniform distribution over 0, 1. Okay, so and I'm asking, is the distribution that has binary support, but the binary support is 0.2 and 0.8, is it a mean preserving contraction of the uniform distribution over 0, 1? The answer is no. Why? Because essentially, and in fact, it has a very nice characterization in case of uniform distributions, which distributions are on a binary actions, which distributions are implementable. By the way, in the paper we have a full characterization for any distribution, but in the case of uniform, it's extremely simple. A binary support distribution is a mean preserving contraction of the uniform distribution over the entire segment, if and only if the distance of these 2 points is at most half of the entire distance. Okay, so since 0.2 and 0.8, their distance is 0.6, which is above 1/2, it is not implementable. You can also have...
Meaning they could be a mean preserving spread, but not a contraction.
You can just... No, you cannot... wait a minute. So can they be a mean preserving spread? Yes, sorry, yes. I think the answer is yes. They can be a mean preserving spread, but not a mean preserving contraction. The intuition for why they cannot be a mean preserving contraction, because right, you want somehow to pull the segment 0, right, starting from 0 to pull it into 0.2, let's say, and then you are stuck when you get to 0.4, right? What will you do with the... You need to put their mass of at least 1/2, right? But if you do so, then you get to the point 0.25, and the expectation is not 0.2, rather it is 0.25.
All right, thanks.
Yeah, and the same here when I say that they are too far from each other. So in the context of the uniform distribution, it simply means that the distance of these 2 points is more than 1/2 of the entire length of this segment. Okay. So essentially, what remains after we guessed the B pooling interval is to try somehow to concatenate it with other pooling intervals and the full information intervals. And the way to do it is essentially we try to play with this tangent point, and it smoothly move, and we stop exactly at the point where it touches the function. This is exactly the point where we stop, and then we have this nice solution that essentially reveals the state here and pulls this state. Okay. Let me give you one last example very quickly. Here is another very nice curve. You can also try to draw all the double tangents. In this case, you will get that only one of them does not violate the fact that only one of them does not violate the fact that these 2 points are not too far from each other. If we try to complement it by in a similar manner to how we did previously, we get this red function. Unfortunately, this is the only way to complement it to the entire segment. Unfortunately, this price function is illegal. Why it's illegal? Because these 2 points, we said one should be above the expectation and the other should be below the expectation. Fortunately, these 2 points are located both below the expectation. So this is not good. What we deduce from that there is no B pooling interval at all for this function. And once we restrict ourselves only to pooling intervals and B-pooling intervals, we can just try to draw this kind of continuation. We first try to do it, let's say, from here. We draw a double tangent, then from here we have a single place to proceed, which is here, and we are stuck. And we can play with this continuum process of trying drawing the function, and essentially after playing with it, you get that this is the solution, that it pulls the 0 y1 to z1, y1 to 1, 2 to z2. It fully reveals the state y2 to y3, and finally it pulls the state y3 to 1 to this point. Okay, so this is the price function. And we got to it because we reduced the number of options from 3, which is pooling, B-pooling, and full information, to just 2, only pooling and B-pooling. Okay, was it a luck that we succeeded to solve the 2 above examples? So it turns out that no, we can formulate a concrete exhaustive search procedure that essentially finds an optimal policy over every smooth functions that switches between concavity and convexity finitely many times. Is this procedure efficient? So in context of, in algorithmic context, no. It exhaustive search over exponentially many of the size of exponential size. But nevertheless, for quite simple examples, namely examples where the function, let's say, switches from concavity to a convexity at most 5 or 7 times, you can try to do it with a pencil and a piece of paper. You can play with these things, and you can actually solve any persuasion. You can play with it and essentially solve any persuasion problem. Yeah. So it's not algorithmically, it's not efficient. Practically, I think you can solve it even for functions, yeah, that switches, let's say 7 times is should be more than enough for any right, for any practical application. But yeah. I have no time to talk about monotonicity in persuasion. Let me finish with an open problem. So we can think, especially in the context of a partially informed sender, it's very natural to ask what happens if the underlying state theta that is right is not binary, but let's say ternary or something above 2. So essentially this question, if we want to try to somehow to apply the same analysis as we did here, the most useful thing will be to understand what are the extreme points of the multidimensional mean preserving contractions. And Marco, I had a talk with Marco on this context, and he referred me to several very interesting kind of negative results in this direction. But so this question was posed. Is not known. It's an open problem kind of to understand the extreme points of multidimensional mean preserving contractions. It's probably quite challenging open problem, but yet I think that also even somehow to give interesting counterexamples in this context, interesting examples of some crazy things that happened there. Try somehow to implement this result in the context of persuasion is an interesting open problem. Okay, thank you.
Thank you, Yakov. Thank you. Are there any questions?
Yes, I would like
Please.
to ask a question. Yakov, in the example you showed us, you always used finitely many intervals.
Yes.
And you said that you can find examples with an infinite number of intervals.
Yeah.
But do you have some idea of what a class of or an interesting class of utility functions for which you can always get an optimal policy with finitely many intervals?
Yes, we have it in the paper. It's it all has to do with the number of switching from concavity to convexity. If the number of switching points is at most n, we know that you will not need more than n, or maybe, if I'm not, maybe 2n intervals. I think we have a formal proof for 2n, but we suspect that it's less, that it's maybe n or even n over 2. But in any case, but you need some linear order of the number of concavity convexity intervals. So this is in the positive side. In the negative side, remember that theorem 2 in the main theorem 2 tells us that every B-pooling policy has it can be the case that it will be the unique solution of some persuasion problem. The way we prove it is by explicitly constructing a utility function for which this is the case. It's not an abstract proof, so you can look at the proof of theorem 2 and it will tell you how to construct kind of counterexamples or complicated examples where you would need, in particular, where you need countably many in the number of intervals.
Okay, thank you.
Any more questions? Okay, if there are no further questions, then we thank Yakov again for this interesting talk.
Thank you.
Okay.